Hi, everyone. Welcome to AI4. I'm super excited to introduce you all to our next speaker. His name is Bataineh. He's the lead data scientist at Humana. Mo, welcome.
Thank you, James. Good afternoon, everyone.
Great. Well, why don't you get started, Mo? We're excited for Black Box Predictive Models Explained. I'll be on here if anybody needs anything.
All right, sure. Thanks. Do you guys see and hear me well? You see the screen?
You look great, Mo.
Okay. All right. Again, thanks everyone for joining this session. And I'm again Mo Bataineh, a lead data scientist at Humana. And today I'm going to be sharing with you guys our journey on a new innovative approach for explaining the predictive models in general and opening that black box and make it explainable and interpretable as well. First, let me just give you this, share with you this slide around Humana. It's one of the biggest health insurance companies in the US. Number 3 or 4, and we are an insurer and healthcare service provider, provide service for focus population is Medicare and senior population, but we also have other line of businesses, commercial, Medicaid, and also the TRICARE or the military and government business. With that, Ben, let me jump quickly to my discussion and my presentation here. First, let me introduce you to this problem that I believe most of data scientists and machine learning researchers, scientists are aware of, which is the black box machine learning, right? All machine learning algorithms are, most of them, I would say, especially those we eventually go with when we build a model, are the best models, but for the compensation or for the trade-off of having them unexplainable because they are complex, right? So what we see eventually is input data, great output, but we don't know anything on how or why this is what it is in terms of predicting probability, class, forecasting, or some regression number. And why this is a problem? And first we said the problem, right? It's you cannot explain it. What's behind the scene? How it came up with this output? Also, there is what we found is there is a very limited work around this particular area. Everybody wants to build machine learning and work data science use cases, but there have been a few interest or a few research around how to explain these models and make them interpretable for end users and the product users, right? So why it's a problem, right? This is a problem. We say it's a problem, but why it's a problem? Because first, it kind of like discredit the model, and there is a lack of credibility on, if you cannot explain what it is, then there is some kind of doubt. Oh, I don't believe this. Why this prediction is this way? I don't know what to do with it, and they will have some doubt around the model, right? Second issue is that also the action or plans. So what part of the picture, right?
Hi, everyone. Thank you for your patience. We're on this right now. Mo, is that you?
Yeah, do you guys hear me now?
Yes.
I'm sorry for that. I don't know what happened. I was still speaking to myself.
It's okay.
Yeah.
All part of normal problems these days. We lost you at why is this a problem?
Okay, but I kind of like, I don't know, where do you guys reach with this?
Sorry, what was that?
Where did you guys reach with me? Like, did you
Yeah,
just
we lost you at
seconds?
what is the problem and why is this a problem? That's where.
Okay. All right. Okay, let me. Okay, I'll continue here. For sake of timing, we'll go to, this is a problem because we said there is a less credibility for, a lack of credibility for the model if it doesn't explain what's going on, right? And also, you have limited action to execute the plans if you don't know what was the reasons behind this, model. And how did we resolve it? We actually came with a new approach, and we developed a new algorithm that's called FIPE, which is Feature Impact for Prediction Explanation. That's explain those predictions at the individual level. That's for each observation, you can see what are the top drivers, that are the top reasons behind that prediction. Kind of an example to share with you guys what we mean here by top drivers. Do you guys still hear me well?
No.
Good. I keep checking on that. And one example here to share with you guys, see, those are three, for example, we have three scores, right? Three scores coming out of the model with the three same exact numbers, 0.95 probability to have some, incidents. For example, go into the ER in the next 30 days or so, right? The top drivers, what it does here, it gives you what are the top driving reasons, what are the top 5 reasons here that are leading to have this person to have 95% chance to go to that ER. And as you see here, the 3 different observations have a 3 different underlying reasons. You can gain some insights from the first person that generally that person is utilized by having multiple ER utilizations. That's the main driver. So there is some kind of like behavioral kind of like going to ER for anything. Second part is person that has generally, there is some respiratory issues that are leading that high reason. So there is a respiratory disease issue that need to be maybe managed or educated or handled better. And the third one is there is some behavioral conditions that driving that high score. So as you can see, the execution plan for each one of these predictions will be totally different if you have these more insights on the reasons on why that prediction was high. Okay, so that's what the top driver will do for you. Now let me introduce why we did this, why we built the feature impact for prediction explanation FIPE. Because first, there was a precedent need from our internal partners and customers within the company that we need to provide with care managers and end users. What are the reasons and driving these high predictions or scores? So there was like a big need for us to seek for top driver implementation. The second thing is also when we search for the literature out there, we found multiple methods around top driver, but actually eventually there are only 2 methods that are going at the top like local level, which is like for each observation, what is at the top driver, which are lime and shape value or shape. And when we compare with them, there is still a very big limitations for these 2 algorithms. And based on that, we went ahead and we came up with a new approach to build the top driver based on our research and understanding of how these predictive models work. But eventually, the model is also model agnostic, though it works in any model. And when we compare it with Lyman Shapley, we overcome some of the problems that they have. For example, there is no need for heuristic settings or some user settings, which make this FIPE approach much more stable in terms of producing these results. Second important thing is actually it's much faster in terms of computational expense, power. Shapley and Lime, if you need to have much more observations to be fed in there, it is going to take forever to complete. And FIPE is, I would say, it needs low computational power to be completed. So obviously, we found a superior performance out of FIPE compared to those existing methods. Let's go ahead on a little bit more details about how we built FIPE. The hypothesis or approach for us was
Thanks for your patience again, everyone. We're getting Mo back on. Hey, Mo, are you there?
Yes, I'm here. Do you guys hear me now?
Yes.
I'm sorry, I don't know what's going on here. I'm so sorry for that.
No worries. We're all on the same boat these days.
Do you guys see my screen now?
Yes. Yeah.
Did you follow everything before this slide, what I said here?
You were just talking about your hypothesis.
Okay, so hypothesis, I would say my hypothesis is kind of like based on understanding the models. Usually, the first fact we kind of approach it with this hypothesis was features who are on their mean value, they're not going to be driving the score. They're not going to be driving, high or low score beyond what you're interested to see, right? If every feature is its mean, then all that beyond also its mean, which is not going to be useful for any execution. Usually, any predictive model, usually it's executed at the higher or the lowest tail end of it. We are interested top 10%, 20%, 30%, or lowest 10%, 1%, and so on and so forth. Generally, the mean value doesn't mean anything for us. We're not executing anything around it. That's why we know that features in general that are beyond their median or mod value, if they are categorical, then they are most probably the driving features. And the second thing is actually the features that are the most varying features, the outliers. They usually have the strongest weight on the target, on the score. And for that, what we came up with this approach is actually understanding how we can calculate the feature impact using individual contribution of that particular feature. That's what we call it. And the second part here is actually the correlation or correlated contribution, which is when we change or shift that feature, or understanding how the feature comes together with the other features, right, together. So those are the two parts that we included in FIPE, and this is the mathematical formula for that. First, we have the impact sign, which is this feature driving the model, driving the score to be positive or negative, right? So that's a positive or negative. It gives the sign for it. And then the second part is actually the individual impact, which is part A here. If you think of this one as the original score, right? Changing the X feature to its median or mod, and then feed it again as a new observation to the model, and rescore will give you a new score, which is SX. The difference here will give you the impact of that feature by only changing that feature back to its normal value, let's say, so to speak. And then the second part, which is a little bit here trickier, is the correlated impact, which is part B. How we calculate the correlated impact is actually by having two new observations. The first one is actually changing all the features except X feature to their median, and then we feed it again as a new score, and we get that value. And then we reference that to the median score, which is the score that's produced by setting all the features to their median. Right? So that means you're wiping out all feature impacts by getting this SM, and then wiping out everything except X by getting SC, and the difference here will give you the correlation, the correlated impact due to having this X value with its value, right? And then these two parts, whichever is bigger, it will have the relay in which direction is impacting that score. And all these feature impacts are normalized by dividing it to the median score to have a same reference for their impact. You guys still hear me well? Great. Okay. Quick example here with shortened time. Here we have three inputs, right? 3 inputs for a prediction model that uses ED department visits, age of the person, and utilization count, which is doctor visits in the past, let's say 60 days or 90 days, right? If you look at these 3 inputs, these are the inputs. ID is the observation or a patient or a member, and that's the value for those 3 features. And this is the prediction that comes out from the model, right? That's the original score, SO. And then we calculate the median score, which is setting everything to their median value, right? This is the median value for the 3 features, and this is the SM, which is the median score. That's one score regardless of the features. And then what we take, let's take as one example, which is ID1, right? Let's only take one ID1, and now we need to create additional features. And here we need to create SX, which is changing that feature, only that feature to its
Apologies again, everyone. We're getting Mo back.
Hey guys, do you hear me again?
Yes, we hear you.
James, do you hear me?
Yes, you're back, Mo.
Hello?
Mo?
Yeah, James, do you hear me?
Yes, you're back on.
Okay, my apology.
No worries.
Okay. Okay, technology. Trying to reshare my application there. Okay, I'm gonna be sharing my entire screen. I cannot find my document here. Do you guys see my screen?
Yes, we see you.
Okay. I was sharing with you guys the example. Did you hear how we created these 2 parts first?
You can go ahead and run over that again.
Okay. We have 3 inputs, right? 3 observations. This ID is a patient or a member, and these are the observations for these 3 features, the feature value, and this is the original score that's coming from the model. And this is the median score when sets every feature to its median value, right? So these are SO and SM that we shared in the previous equation. And then here we take only one ID, right? ID1, and we need to create 2 additional observations for changing one of each features, like age. When we change age and create SX, that means changing age to its median value. So we're changing age from 62 to 66, and then we leave everything the same. We pass it again through the model, and we rescore it. This is the new score. Same thing when we create SC, which changing all the other features to their median value, right? And then we keep age with the same original value. And then based on these 2 new observations, we can calculate the impact for age. And the same thing we did for ED visits and utilization counts. You guys still hear me well? James, do you still hear me? Guys, do you hear me? Hello, do you guys hear me? Okay. Okay, I'll continue, sorry. Okay. I'll move on to the next slide, which is, to the next part, which is we calculate the impact eventually, and then after that, we get the ranking for each one of these features. So eventually the impact there is, you calculate that feature value impact based on this mathematical equation, and then we then rank them, and you see the rank here, ED number first, number 1, and then the utilization number 2, and age is number 3 here. And based on that, we get that ranking. Now, just finally here, the pros and cons for FIPE. FIPE obviously is fast implemented algorithm. We already implemented in multiple platforms: Spark, SAS, Python. It also fast running, and also it covers actionable insights, because it actually tackles the features that have some abnormal values or beyond the mean value. So that means it can be done something on it. And obviously there is no heuristic, so you can reproduce the same results over and over again. You don't have to change anything, and that make it also reliable. And the only limitation you see it for FIPE is actually for some observation. If they're all their values are right on their median value, then their top driver will be 0. They're not going to be having a top driver because it isn't going to create any impact, which makes sense, because obviously we're not going to need to do any action. You can go back to the original global level kind of feature impact or importance, and then you can use them as the guidance. Do you guys still hear me here? Do you guys hear me? Somebody say yes, please. Okay, I have to stop and come back. Okay, do you guys hear me now? Okay. All right. So I guess we're short in time. So first, the next step is finally. This is the next step. We're gonna be getting end user kind of feedback, which is impactful or not, and then that will change kind of the top drivers kind of display. And then the next step will be recommendation system. If we know who is having this high score, why, which is it through top driver, what are the top drivers, the top reasons, the next thing will be so what, or what's next, how we can do some actions. So the next step will be building AI recommendation system based on the top driver combinations and recommendation that could be insightful and actionable based on individualized and kind of like different cohort levels. With that being said, I think that's all I have. I'll leave 2-3 minutes for questions. So if anyone have a question, please go ahead and ask. Okay. Now I see. Have you considered using Python package random forest importance? Yes, random forest actually is. Do you guys hear me? I want to make sure you guys hear me well. You guys hear me? Okay, if you guys can hear me, random forest is actually just a global importance level. That's what it produces. It doesn't produce a local importance, right? This method is model agnostic, that produce at the member level, like at ID level. Each ID have a top driver. Random forest only give you an overview of an over-level picture of what's going on with the model, what are the top features in terms of the global level, not the local level like here, okay? Okay, now other question. Yeah, I'll share the slides if you guys want that. Let me see. What other questions do you guys have? Trying to see if there's any. Yeah, you change the features one by one and you create those additional scores for them. And eventually that will help you get the impact for each one of these features. I guess I don't see any other question. If you guys have any other question, let me know. Okay, I'll share with you guys the slides. Thank you so much for your time, and I hope you have a good day. I'm sorry again for having this interruption. You all have a good one. Do you guys still hear me? If you guys still hear me, I would love to answer these last two questions. Yeah, if you guys hear me, it seems there is some lag on that and seeing your answers. So recommendations, use cases of how to use the top drivers for actionable items. Yes, that's an ongoing research. And top drivers, displaying those top drivers in groups, grouping them could help creating those recommendation systems. It's still on.